Okay, in that case, let's continue with our exposition of Fourier analysis. So in the last lecture, we derived the Parseval formula. Okay. I like this bigger grid. So we have a function that satisfies the Dirichlet condition, and its L2 norm is given by the sum of all the coefficients, the Fourier coefficient squared. Okay, so this was Parseval's formula, and this was valid for all functions within a class which can be expressed as a Fourier series. Okay, so the CNs, what are the CNs? The CNs measure the strength, with which a certain function or basis function e to the power 2 pi I x n L over L, contributes to phi of x, right? So this is basically saying that the CNs, they are telling you what is the strength with which that pure sine wave is contributing. Okay.
Is it like an amplitude?
It is an amplitude, yeah. It is an amplitude for that particular pure sine wave. That's it. That's exactly what it is. So, for example, for some function, you might find when you do the when you work out what the CNs are. CNs are, of course, you can find something like this, right? For n equals to 1, and then, sorry. 2, 3, 4, 5. In principle, there are an infinite number of these things. But for some particular function, there may just be a finite number. But, the amplitude would be such that, this sum would be a convergent sum. This sum would be convergent sum. Okay. So this is the interpretation of the right-hand side of the one interpretation of Parseval's formula. Now let's rewrite the right-hand side. So the right-hand side goes from minus infinity to plus infinity, then Cn squared, and let us write delta n here. What is delta n? Delta n is a fancy way of writing 1. Okay. So this is what delta n is. Now let's introduce delta k to be 2 pi by L times delta n. Okay. So this is what we define to be delta k. So then, and then, we can, k would be defined by 2 pi L by n. So then our right-hand side of Parseval's formula becomes, we are going to take some funny limit now. So I'm going to express this in terms of k. So we have this very interesting way of writing 1. And what we will do is that we will take, at some point, L going to infinity limit, k going, delta k going to 0 limit, but in a way that the whole thing remains 1. Okay? So now Parseval's formula looks like minus L by 2 plus L by 2. There was a 1 over L here, but we can take it to the other side. If I take it to the other side, now there's a sum over n from minus infinity to plus infinity. And now we have an L squared, but let me take that L inside the modulus, then the Cn. And here we have square root of 2 pi, then the whole thing, mod squared, times delta k. Okay, so this is, we haven't really done anything new. All we have done is define delta k and rewritten everything in terms of delta k.
Sir, shouldn't it be root over L?
No, because there's an L.
Oh, yeah,
There's
sorry,
an L
sorry.
here already. Yeah, okay. And there was a 1 over L here, right? So yeah, okay. So now let me define AL, which is a function of k, to be LCN divided by square root of 2 pi. And if I express the, remember that Cn had an integral expression. If I use that expression, then my this becomes 1 over 2 pi, because there was a 1 over L in that expression. And then this integral becomes from minus L by 2 to plus L by 2 phi of x e to the power minus I kx dx. Here, what I've done is that I've replaced the 2 pi n over L by k according to this definition, okay? So this is the definition of AL. Now we take a limit. We take a limit in which L, the periodicity, the period of the function becomes infinite. In that limit, k goes to 0. Of course, this was always on the cards because, we didn't want to just express a function which was periodic, right? Our wave function is not something periodic. A realistic wave packet is something that has a finite width in space, right? And also probably in time. So we always wanted to take a function in which L was infinite. So, so we take that limit. In that limit, we call A of L just A of K. And then this becomes the limit is delta k goes to 0, not k goes to 0, okay? Yeah, so in that limit where L goes to infinity, AL of k, then my thing becomes 1 over 2 pi minus infinity to plus infinity, phi of x e to the power minus I kx dx. Okay? So this is AK.
Sir, the del k goes to 0. Does that affect the AK?
Yes, of course it does. I mean, when you're taking L going to infinity, your function is changing, right? So, this is kind of a formal limit we are taking. We are changing the function, and there has to be certain criteria that the function has to satisfy, right? So in that, yeah, I mean, this thing is changing and the L going to infinity limit, right?
Okay.
Yeah. Okay, so let me just write this over here. A of k is 1 over 2 pi square root. This is conventional, from minus infinity to plus infinity. Whatever the function becomes in that limit, e to the power minus I k d of x, okay? So this is basically what was Cn. Now becomes this nice thing. On the other hand, if I look at my original function before I took the limit, phi of x was from minus infinity to plus infinity, n went from minus infinity, and there was a Cn, and e to the power I, this is a plus, which is important, 2 pi nx over L. Okay. Now, if I take L going to infinity here, then what happens is that phi of x becomes one over, and you have to use the integral expression for Cn here. What is tar C? Sorry, reassert. Farhan, you're sending all these messages. I'm not really sure what you're saying.
So Saif said he can't hear you, so I said restart tab.
What? Also, ঠিক আছে, okay. Okay, so can everyone hear me?
Oh yeah, I restarted my tab, then it started
Okay,
working.
awesome. All right, cool. So, okay, so in that limit, phi of x becomes an integral from minus infinity to plus infinity of a of x, sorry, not a of x, a of k, okay, e to the power plus I kx dk, okay? Now this is not hard, but show this by starting here and using the expression for Cn, the integral expression that we have over here, and then taking the limit, L goes to infinity and delta K goes to 0. Okay. So this way, we can say that in the limit, so, oh, what is this? This is very thick. Maybe it's not bad. Let me try this, okay? So, okay, this is good. In the limit, where L goes to infinity and delta K goes to 0, what we find is that phi of x becomes our function psi of x, because now that there is no need for periodicity, right? Because our function now spans the whole of the real line. Okay, so in that limit, we go back to our original function, psi of x, and it's given by 1 over square root of 2 pi minus infinity to plus infinity, a of k, e to the power plus I kx, d of x, not d of x, d of k, right? And then a of k, on the other hand, is 1 over square root of 2 pi, integral from minus infinity to plus infinity, psi of x e to the power minus I kx, d of x. Okay, so notice the sign difference. Okay.